Looks like we can go ahead and get started. Thanks for coming, everyone. Today we have Bryan Ramson. I'm certainly going to miss some of his previous path through physics because it's been quite an interesting one. But he started out with his undergrad at Howard doing math and physics, and then Michigan for grad school, doing some climate and atmospheric science, and also some particle physics / nuclear physics on the Sequest experiment. Did a stint at NASA visiting for a bit, and now after a postdoc at Fermilab is an associate scientist. He's going to tell us about the new era of precision neutrino physics. So go ahead, Bryan, take it away.
Yep. I don't need a mic or anything, do I?
No, you should be good.
Okay.
The room mics will pick you up for
Probably after a minute. All right. So this might be a bit infantile, but what I typically do before talks, especially talks after lunch, is I have an exercise, and that's a breathing exercise to make sure everybody stays awake. So we're gonna get up, stand up. We do 3 breaths. I do this with everybody, including my students. We take 3 basically yoga breaths. Make sure you're in the room, make sure you're awake. Let's do the first one. Out. Yep, you should have just got that oxygen hit to your head. Yep. Let's do the second one. Okay, out. Let's do the last one. All right, everybody have a seat. So one of the reasons I really wanted to come here is because one of the things I'm pitching to the field, the HCP, so a little bit of background, there's an artificial division between nuclear physics from a funding source and high energy particle physics. And in neutrinos, we're getting to the point where we need to be able to do nuclear physics to do our experiment. We have somehow put the results from $1 billion experiment, we put nuclear physics in between us and those results. And one of the things I'd really like to do is solve it. So this is sort of a roadmap to how we're going to solve it. So I'm going to give you sort of where we are, what we're doing, why we're doing it, and then my solution, which is a bubble chamber. And I'll walk you through how bubble chambers work. So first, introduction to neutrinos. If you guys are not familiar with neutrinos, major things you need to understand are that there are these guys up here. They are leptons, but they only interact using the weak bosons. Because the weak bosons are massive, that means their interaction length is fairly short. And that means these guys basically don't interact very often with the rest of regular matter. So if you look at this plot, which is a charge current neutrino cross-section on neutral currents here as well, what you should be able to see is that, yeah, you got this great line going all the way up. But if you look at the y-axis, this cross-section is 10 to the negative 38. If you compare that to something like an electron, I think that's off by about 12 or 13 orders of magnitude. So your ability to observe neutrinos is significantly reduced compared to everything else. That means it's very difficult to measure. I say that neutrinos are basically matter phobic. Why we care about neutrinos, we can start with this charge current Lagrangian density here. So how many people just got out of QFT? Okay, got W boson here. You got your leptons, you got this gamma matrix, you got your neutrino. What this is essentially telling you, so this is a vertex. What this is essentially telling you is that when you're interacting with a neutrino of a particular flavor state, you're interacting with a neutrino in a superposition of mass states. This is an extended quantum effect. And what that means is that you can produce neutrinos of a particular flavor, and because it's a superposition of mass states, those energies beat against each other as the neutrino moves through space and time. And then you can sort of measure it at a different location and have an enhanced chance of measuring a neutrino of a different flavor, even though that is supposedly the same neutrino. This is called oscillation. So you can think about it mathematically. If you only have 2 neutrinos, let's say you have only an electron and muon neutrino. This is not the case. Obviously, we know we have tau neutrinos. You can think of the transition between these 2 guys. You can sort of encode that in a single parameter, which is sort of like a 2-dimensional rotation. So you can encode that with an Euler matrix. I'm sorry, an Euler angle, 2-dimensional Euler angle. Call it a day, you're done, right? Let's assume you have 3 neutrino flavors now. Now you're doing the rotation instead of in 2 dimensions, you're doing it in 3 dimensions. which means you need to move from one angle to three angles. So when we're looking to try to resolve this PM&S matrix, which describes, it's essentially called the lepton mixing matrix, you can break those Euler angles down into neutrinos from a particular source. You can measure each one of these individual sources. If you measure those well enough, you get access to a fourth parameter called delta Cp. And delta Cp describes the difference between neutrinos and antineutrinos, which is essentially the difference between matter in the leptonic sector and antimatter in the leptonic sector. Also, while you're doing this, if you do the math, you actually care about the mass splitting. So basically those mass states that are beating against each other, you care about those. And it turns out that we don't know whether the third mass state is heavier or lighter than the other two. So we're also trying to resolve that while we do this mixing matrix, while we try to resolve this mixing matrix. So this is about how well we're doing. This is everything about 3 sigma. And as you can see, theta 1, 2 is doing okay. This is 3% level on theta 1, 2, theta 2, 3, theta 1, 3, and even the mass splittings, 3% level, right? But you also see that there are 2 columns here. And that's because we don't know, again, whether that third mass state is heavier or lighter than the other one. And if it's heavier, then that's considered normal ordering. If it's lighter, then that's considered inverted ordering. So that indicates that there's a large uncertainty on that. And there's also a large uncertainty on this fourth parameter that we're trying to get, which is delta Cp. So this whole idea of moving to the new era of precision neutrino measurements, it's literally saying we're measuring neutrinos well enough as they oscillate to resolve delta Cp. Hope everybody's with me. Good? Cool. So how do we do an oscillations analysis? Well, first, you need 2 detectors. And this is the critical equation that you're working with. This is your yield, the number of neutrinos of a particular flavor at a particular energy spectrum. It's your probability of oscillation. It's your cross-section, your flux, and your efficiency of your detector. And essentially what we do on experiments like NOvA, because there are experiments that are long baseline oscillations, experiments that are not like NOvA, is we start with our near detector, and we essentially simulate, we compare that simulation to the data that we measure, and then we essentially do an unfolding matrix. We unfold in the true space, we compare that again to what we've measured, and then we compare the near detector to the far detector in Monte Carlo. And the things that change between there are flux, efficiencies. The flux is actually quite different because you're sampling different parts of the beam as you move further away. Think of it like a flashlight. If you're closer to the flashlight, you're going to observe different parts of the beam if you put something farther away. Hope that makes sense. So then we refold, not refold, we look at our comparison between the near detector and the far detector. We throw some values for a probability of neutrino oscillation. Then we refold that through, and then we compare to what we see at the far detector. This is a particular way of doing it. It's called like a forward folding thing. You're only able to do this when you have neutrino detectors that have the same type of nuclear target. There's a reason for that, which we'll get into. The critical things you need to know about this are the things you care about, again, are your flux, which come into account here, your efficiencies, come into account here, here, and here. Oh, flux is also here too, and your cross sections. These things affect all long baseline oscillation experiments. So now we can talk about the current generation of long baseline experiments. So there are 2. NOvA has an analysis style like the one I showed you. There's also T2K. There are slight differences. NOvA is at a slightly higher energy. It also has, again, two of the same type of detectors. They use the liquid scintillator, then the target is mostly carbon. And then there's T2K, which has a near detector that is close to a beam in Japan called JParc, or is produced by JParc. And then they have, their far detector is water-based, gadolinium-doped scintillator. And they're a Cherenkov type of detector. But the idea is that you can make the same sorts of measurements with these 2 types of detectors, even though they're at different baselines, and even though they're at different energies. That's essentially what we're doing now. This is the current generation of long baseline oscillation experiments. This is one of the major results that have come out as of Neutrino 2020, and the analysis looks fairly similar for Neutrino 2022. Neutrino 2024 is actually happening in June. We have tons of new results. I can't show them. For example, we have a joint analysis between these two guys, but let me get into what this graph is telling you. If you haven't seen this before, it could be confusing. You have theta 2,3, or sine squared theta 2,3, which is again one of those Euler mixing angles. And then you have delta CP. And again, we're trying to really measure this. What you're seeing is that the value from NOvA, the best fit for our analysis, and the value from T2K are basically giving us two different answers for delta CP. They're literally saying that matter and antimatter behaves completely opposite to each other, right? But if you look at the uncertainties, you see that even though the best fits are in tension, the uncertainties mean that the actual measurements aren't in tension. That's because these measurements need more statistics in order to become statistically significant, or have some sort of sigma associated with it. This is currently where we are. This is the best we can do.
It's just a coincidence then that the area is ruled out, the legs just happens to fit in the pocket.
So the reason I like this graph, so this was like a whole thing, right? So even though we work together, we're like kind of competing, right? I think a lot of experiments do this, right? But they released their result first because of the type of detector they had, and we came and we're like, ours is exactly opposite. Like it was kind of like a competition thing. It was kind of funny. But yes, to answer your question, it is like chance. So
Brian, you said the results are embargoed at the moment. Can you say statistically whether there are better statistics and even how much?
So what we do is when we combine the two experiments, we basically do a completely new analysis that sort of tries to redefine analysis objects such that they are equivalent for both. And that allows us to combine the statistics from both experiments, which does give us a slightly better preference for a particular value. If I meet you in your office, we can talk about it. Later on, we can talk about what that value is.
But does that mean that you end up with only one data point?
Mm-hmm.
Okay.
Yep.
So now then you'll have three data.
Well, yes, but the data point from the combined analysis should agree with both of these, right? So this is just basically if we combine and what's up? What's up?
For me, no, I said if you combine them and they should agree, then I can imagine where it might be. I don't want to bother you anymore.
No, it's great. So then let's talk about where the uncertainties are. We see that, how much we know about our detector is a large uncertainty statistically. How much we know about neutrons. Neutrons are always a big problem in neutrinos. And then when we come down to third, it's for our neutrino cross section. This is for assuming you add everything together with PT, or if you do PT extrapolation, which means you bin everything out PT. Things are slightly different. What you see is the uncertainty is mostly statistical, but you see where the uncertainties are coming from. And this is just on theta 2,3 and delta M32 squared. So that's essentially the mass ordering and theta 2,3. Oh. And this is where we come to the crux of when we talk about precision in neutrinos. So if you look at the uncertainties in delta CP, the thing we really want to measure, what you see is that, yes, our understanding of the detector and its calibration really comes into play. But the second guy here are our neutrino cross sections. And it's on both experiments. It's on T2K, which says it's combined about 3 to 4%. And on NOvA, the experiment I'm on, I'm actually one of the people who is in charge of neutrino cross sections on NOvA. I would say we have about 19% of the total systematic budget is just to neutrino cross section. So given that we expect to move into a new era of precision, what do we do about this? Well, talk about what the problem is, or where is the problem? So this is a famous plot and a review of neutrino cross sections and interactions. This is a charge current neutrino cross section divided by bins of energy, and this is bins of neutrino energy. Now, the reason this is so hard is because if you're thinking about heavy ion physics, right? If you're doing, what is it? I guess ion and ion. You guys don't do DIS, right? You typically look at gluon-gluon fusion or quark-antiquark annihilation, that sort of thing. Mostly gluon-gluon fusion, all right? Right? Yeah. But if you're looking at neutrinos, at least at the energy scale that we've chosen, you have to deal with at minimum 3 different processes to get to your total interaction cross section. So that's quasi-elastic scattering. And then the reason I'm defining this is because it's defined differently in neutrino than it is in nuclear physics. So you got quasi-elastic scattering, where you essentially bounce a neutrino off a nucleon, and then the nucleon pops out different energy. You've got resonant production, which is where the neutrino forms like a bound state with the nucleon. And then a delta is typically produced, a delta baryon, and then that decays. But sometimes that delta is virtual. You also have deep inelastic scattering, which is different. Deep inelastic scattering just means we see things that are probably not these two. It is not the same as deep inelastic scattering for nuclear physics, because the nuclear recoil in deep inelastic scattering for high energy physics is typically way higher than it is when we think about it. So for the stuff that is normally considered to be nuclear physics, at least high energy nuclear physics, the nuclear recoil is so bad that you essentially blow the nucleon apart. But here you just hit it really hard, and sometimes it falls apart, sometimes it doesn't. You also have meson exchange currents, which is you're hitting a pair of entangled nucleons, and that has particular effects as well. But on top of having to really figure out what's happening with this linear combination of interaction processes, you also have to think about the actual nuclear medium and what happens when you produce hadrons and then they actually have to get out of the nucleus. The way in which we deal with physics and neutrinos, we convolve these. That makes our life super hard. Right? We deal with it in simulation, we deal with it separately, but even the approximations we use, they don't work all that well. So one way you can solve this is to look at old bubble chamber data. So we did this. We pulled bubble chamber data from Brookhaven, Argonne, Bepsch, which is the older guy, like the upgrade to Gargamel. The Fermilab 15-footer, which is the biggest one ever made. I actually don't remember what SCAT is. But if you see, these energies are way higher than what I just showed you. And the only ones with energies directly where we're currently measuring now are the Argonne bubble chamber and the Brookhaven bubble chamber. And if you're looking at these red and blue points, what you see is that there's significant systematic uncertainties. These points say that you're looking at something completely different, despite the fact that you're measuring the same neutrino interaction. And this is for multiple processes. And then you look at the number of data points that are actually produced or that you're actually reanalyzing, and you see it's only about 10,000 points total. 10 to the 4. Was it 10,000? Yeah. 10 to the 4 data points are gonna supposedly lead us into the era of precision neutrino physics. I think that's gonna be hard to do. So one of the ways we put this into practice is we use something known as a generator. You guys do the same thing and heavy ion stuff. And our neutrino generators just do not have the exclusionary power to actually decide between which models are correct and which ones aren't. So we essentially have to do model spread to even start to think about how we're going to work on this. And obviously, just because you do a spread of models doesn't mean you're actually considering the uncertainty in the proper dimensions, right? So a lot of work to do. So what happens if you do it incorrectly? So we have tried to do these cross sections. And what you're seeing here, this is the total cross section. This is the quasi-elastic portion. And these green points, which I want you to pay attention to these actual, the actual icons, what are they called, graphics?
Marcus.
Markers, thank you, symbols. These guys are all on deuterium. And if you look at the orange ones, these are more recent measurements. For example, this guy is from 2010, but it's made on carbon. So you look at this gray guy, and look out here, right? It's a huge issue. What this is indicating is that one of the ways that we do diagnostics for our measurements is just completely not working correctly when we do these measurements on carbon. And that's called the axial mass. When we do our form factors, when we think about neutrinos, we essentially do a dipole ansatz for the axial mass, for the axial vector form factor. And the value of this should be 1 if it's diagnostically correct. And what we're seeing for carbon is that it's 30% off that value that it should be. This is a mistake. You gotta do something about this. And of course, NOvA has taken a look at this, they've gone back and reanalyzed, they think it could be coming from MEC. But that indicates that you have to now do what's known as a tune to your cross-section to get it to match what is understood about the field.
Right, I'm sorry. Is this a line of fit or a generator?
This is a generator. Oh, I missed the slide. Oh, no, there's a really good slide around here that I wanted to show. Ah, okay, I went too far. All right, so the slides are slightly out of order, but, well, no, let's continue. Okay, so this is what happens when you get it wrong. So now we can talk about the next generation of long baseline experiments. So first is Hyper-Kamiokande. I'm just going to tell you what it is. I'm not a member of this. I'm not going to talk like an expert. What I can tell you is essentially Super Kamiokande, which is the bar detector for T2K, is much bigger. 5 times as much water. It's the same, it's essentially the same design. All these are PMTs. And then what they're going to look for are the PM&S matrix variables. Because there are so many nucleons in one space, you get some questions, or you can answer some questions about proton decay. And you also can do like multi-messenger astronomy. You can look for supernovas, neutrinos for supernovas, pretty awesome. And then we also have DUNE, which is the US Future Long Baseline Oscillation Experiment, which I am an expert on. And obviously you have a new detector, a fire detector, you got some dinosaurs. This is just to make sure you're paying attention. This obviously is a neutrino beam. This was an April Fool's joke where they said, you know, the neutrinos are going through dinosaurs, and they probably are. But you're looking at the same things essentially. So we have 2 experiments that are designed to do essentially the same thing. So we've talked about we need statistics to get to our precision error, right? So this is one of the ways we're going to get statistics. We're going to get a really great beam, which I'm going to talk about in a bit. And then we're also going to have these giant detectors, right? So you saw how big Hyper-K was. Hyper-K is 260,000 tons. I think the fiducial mass is 190,000 tons. This is much smaller. This is about the size of a football field, and it's about 2 miles underground, and there'll be 4 of them. But it's way better instrumented than what I believe Hyper-Kamiokande will do. The idea is that we're putting in a lot of work to make sure we can get the statistics. This is sort of one. This is called proto-DUNE. It's a prototype of DUNE, or the DUNE far detector. One of these guys is 8 feet tall, and is half of this right there. So actually, two of these guys stacked on top to get one of these things. And this is all full of liquid argon. So it's all cooled to I think 120 Kelvin, something like that. Pretty big.
I have a basic question. How big is the beam when it gets there?
What do you mean? How big is it?
How far spread around are the neutrinos that are going back?
That's a really good question. I don't think we will know how big the beam is until we try to measure it. It's a neutrino beam, right? So we can simulate it, but we actually don't know the true dispersion relation until we actually turn it on. So we know this thing will work. We have planned an ensemble. I mean, we've made this thing work 3 or 4 years ago. We did an ensemble study. We showed that technology works way better than we think it will. And this is what happens if we get the actual things that we want out of the experiment. So these are staged years of exposure. And the things that we were talking about earlier for the PM&S matrix, the mass ordering, this is CP violation, and delta CP. You can see that we can either do exclusion and or get pretty significant measurements in about 2 decades at the max. And this is assuming we have all 4 detectors ready to go. All right. So again, this is what we mean this is why we need to get through the precision error. In order to even start thinking about how to measure delta CP, we need to do something that size with super intense beam for years. So this is the DUNE detector. This is one of the things that will enable us to characterize the beam, like you asked. It's actually what I would consider to be a Swiss Army knife of neutrino detectors. So everything here, except for this, is argon. That's because you need the same nuclear target, but you also have a liquid argon for density, a liquid argon detector, and you have the gaseous argon detector, so you can do multiple scattering, find out things about your final state interactions. And this is a magnet, essentially, that goes inside here as well. And you also have a system for on-axis neutrino detection, which essentially is a beam monitor that's always on axis, so you can always know what your exposure looks like. And this is the distribution of events as a function of elasticity and neutrino energy. And what I want you to look here at is at this z-axis. What you're seeing here is 10 to the 2 times 10 to the 3 is what each one of these bends are. So if you go back, and we see our near detector here is 10 to the 5 events total. What you're seeing here is 10 to the 5 events, 1 bend. So we're gonna have so much data. It's gonna be what I've heard some physicists throw around it, effectively infinite statistics. And this is what I mean when I say we're going to the precision era. We will finally have enough data with neutrinos to do some really interesting things. In addition to just the sheer amount of data, we're also gonna really clearly characterize the beam. So this goes back to your question about how big is it? In order to effectively characterize the beam, when I say this guy is a Swiss Army knife detector, it moves off axis, allows us to sample the beam at different places off axis so we can actually measure the dispersion. This also allows us to get a 1% normalization on the total flux, as well as the distribution of that flux. So the shape and the total amount. So we're doing a lot of work to make sure that we are really backing up this idea of precision physics. Oh, and then I forgot, yeah, there's also a possibility that we'll double the energy. We might also double the intensity frontier. Not the intensity frontier, the actual intensity of the beam, depending upon how favorable our funding profile is. So what happens if you, again, I showed you one type of misunderstanding or one type of thing that one type of mistake you might make if you don't do analysis correctly. But let's say we have infinite statistics. Let's try to do this data-driven correction using the DUNE near detector and try to do an experiment. So this is one of the things we do in NOvA. So because we know that our neutrino cross-sections do not match probably what's happening in nature, or at least it does not have the precision, not the precision, the uncertainty is so high that you can fit a lot of things in between the difference between what you measure and what you simulate. What we do is we do what's known as a tune. I think I talked about tunes a little bit earlier, and we tune directly in MEC. So this is what comes out of the box, and this is what we tune to directly in MEC. And we tune in true energy and true momentum. And this is what our phase space looks like before we tune, and what our phase space looks like after we tune. We can do the same thing with DUNE, and it will give us internally self-consistent results. But what happens if you do this sort of thing with every experiment? What happens when the number of neutrinos you say are coming out of each of the experiment, despite the fact that you're supposedly using the same theory, doesn't agree? It means you have a fundamental conflict in the underlying physics, which means you're not really contributing information to the overall field, right? And this is a really difficult thing to pick out because what you're measuring could look unbiased, but you wouldn't know that if you were biased or not. And this is what I mean. As an example, a graduate student at U Chicago did this sort of measurement. Now, this is a little bit, what's the word I want to say here? Contrived, I guess the word would be. You would not do this analysis this way. What she did is she took our tuning method here and she applied it to a search for new physics. So let's say we're looking for a sterile neutrino. That's what this means, that we're looking for a neutrino that goes from the first mass state to the fourth mass state, or that has some connection between the two. We're looking for that mass splitting, but we don't know what the energy of that mass splitting is. So it could be at 2 eV squared, or it could be at 5 eV squared. If we start with our input parameter here, and we use 2 different generators, and we tune one, and then this essentially perform a closure test, that closure test loses sensitivity as we move to lower energy, which is what we're seeing here. So here, passes the closure test using our tuning method, and here it doesn't. And what this tells us is that we could do something, again, that looked internally self-consistent, but we would not know we were biased. And when we tried to go to compare to other experiments, we would get completely different results. So that should add new context to what I showed you earlier from NOvA and T2K, right? Because we're both doing tuning. So if we're getting completely different answers, what's really good, you know? So how do we fix this? I say we need to get hydrogen into our next generation of detectors. We have this great near detector. We have the system for on-axis neutrino detection. We have this gaseous argon TPC. This actually, I believe, has CH2 in it, not CH, but you essentially double the amount of hydrogen you could be scattering from. The gaseous argon has methane, which has 4 hydrogens in it per carbon. And I think these are great ideas. I think you'll get tons of statistics. What you're going to have to do at the end is some really complicated background subtraction. And you're still going to have your convolved model, as well as your convolved uncertainties and flux that you have to deal with. So I say, in addition to doing these two things, we should also do a dedicated bubble chamber detector. And that way we can finally guarantee that everything we see is self-consistent. So let's say we only do these two. One of the things you have to do is something known as a transverse kinematic imbalance type analysis. It's very similar to this, somewhat to the single spin asymmetry analysis done in heavy ion physics, if you guys know those. You essentially add up all the transverse momentum, and then you essentially look for your missing energy. And if you plot that in the bulk, you can do some cuts that allow you to pick out your sample with very little transverse momentum. And that would ostensibly be your hydrogen measurement. So this has been multiplied by a factor of 10, or reduced by a factor of 10. And this is your deuterium sample. So technically you can do both with TKI, but I don't want to do this because if you're selecting on transverse momentum, you're blunting your quark degrees of freedom, which will become useful later. And you still have these giant uncertainties you have to deal with when you do your subtraction, which means you're bringing in model dependence, which means you're bringing in your flux uncertainties. So it's not quite clear to me that you will get the precision you need to actually solve the problem. So when we try to do one of these experiments, again, this is something that comes from an experiment called the NOvA, which is essentially, it's literally a fixed target 10 GeV neutrino experiment. And they have done the CH-like, where they've extracted the hydrogen from it. NOvA produces millions of events. And after their analysis cuts, this is transverse momentum. Essentially, they project the neutron. So this is anti-neutrino on hydrogen. So you pop out a neutrino, not a neutrino, a neutron, and you can't quite track that neutron. So you have to guess where the neutron is and look for a range around that. And that is one of the transverse momentum things you have to do. That's what that is. And if you do this in 2 dimensions, you can make an analysis cut, which then you can make your background subtraction on. So you go from millions of events to 5,000 that your measurements made on, if you try to do some sort of like event subtraction. And this is a great measurement, right? This is 5,000 events. This is half of all the existing neutrino events that we currently have to go with, right? And this analysis was released last year. It's a tour de force analysis. One of the coolest things I've seen, right? But it's just not going to be enough if we want to move to 1% precision. So let's motivate it a bit more. We can start to think about the event rate that can come through if we put a bubble chamber, if we put hydrogen in near detector, well, it's called LBNF beam, but in near detector beam, the same beam. This is the flux. I'm sorry, this is not the flux, this is the yield as a function of neutrino energy. This is for the what's called FHC, or forward foreign current, which you can think of as basically neutrino beam, even though it's not completely neutrino beam, and reverse foreign current, which is essentially anti-neutrino beam, even though it's not completely anti-neutrinos. And if you do those calculations, if you put a hydrogen detector in this beam, you get about 60,000 events per ton at perfect efficiency. So give you some sense of scale. The Fermilab 15-foot, the biggest one we ever made was 2.25 ton. So, and again, this is 60,000 events per year. So we can easily get into the 10 to the 6 if we run this thing for a lifetime of 10, which we go from 10,000 events to 1 million, which I think is enough. So let's talk about how we're going to build a tiny prototype. So I remember I asked you guys if you know how bubble chambers work, or did I ask you guys? You guys know how bubble chambers work? Anybody want to explain this one? No? Okay. So this is the schematic of the 15-footer. Again, this is the biggest one ever made. If you look at the graphic on the advertisement for the talk, this is the same bubble chamber. So you got cameras up top. These are like literally old-fashioned movie cameras with analog film. They were thinking about doing some laser holography, which I probably won't talk about, but it's also something I'm thinking about. And the critical things you need are this inner chamber. You have this magnet here. This is a superconducting magnet. And then you have this vessel. And the reason you need all this is because you need this to be a superheated liquid, which means it needs to be hotter than its boiling temperature without actually boiling. The way you do that is you compress it with this piston. And when you want to observe an event, you release the piston, the superheated liquid should have some disturbance from charged particles entering the working fluid, and that gives you bubbles, and those bubbles should be in a track. Take a photographic picture, voila, you've got events. So thermodynamically, what this looks like, you start high pressure, low volume. This is liquid, superheated, you're well below the critical temperature. And then you open the volume, and you go to this point right here, which is along the liquid saturation curve. If you do it correctly, you'll go below the liquid saturation curve and have a controlled rise. And this is the portion we want to be in if we're doing it correctly. If you're doing it incorrectly, you start here and you essentially boil the vapor saturation curve, and then you're essentially boiled off. The reason we care, the reason this is super cool, one of the reasons it's super cool is because in addition to just being able to get the sheer density of material we need to do the measurement, we also get a tunable medium. So you can change essentially the state of the working fluid, and you can get different responses from your bubble chamber, which I don't, can we do that with digital detectors these days? I don't know. I haven't seen an example of it. Maybe I just don't have enough experience. But I literally mean, if you need a bigger bubble, you can work at a slightly lower temperature, a slightly lower pressure, and get a larger bubble. Or if you want to increase your ability to sample energy in your medium, you can increase the bubble density, and that gives you literally more samples per centimeter. And all you have to do is probe your working fluid to see what results you get out of it. So one of the other reasons I thought this was a great idea is because we already have a current generation of bubble chambers. They just don't do this sort of physics anymore. They do dark matter physics. And what this means is that these bubble chambers operate in a completely different thermodynamic state than the ones that we used to do those sorts of measurements in the past. So they're typically higher pressure, higher temperature, and they typically use different working fluids. This is some sort of fluorocarbon mixture. And because they operate at different energies too, and at different temperatures and pressures, they can remain metastable much longer than the older style. These guys were designed to cycle multiple times a second. And this thing is huge. This thing is like multiple tons. Here we go. Sensitive time on the order of milliseconds. This is the sensitive time right here. Right there. This guy stays sensitive for 30 minutes to an hour at a time. And it's slowly varying the piston. Very quiet environment so that you can observe nuclear recoils from possible dark matter. And this thing, but because this is a different style of detector, it's also given me, new ideas for how to apply the new technology they find out, right? So one is because they're so quiet, they can use acoustic sensors. And they're so precise that they can identify the different modes or the different alphas produced in different portions of the decay chain of radon, right? So they can just listen to the bubble and they can tell you exactly which alpha or the energy of the alpha particle, which allows you to tell you exactly which part of the decay chain you're at when you put in something like a test, a radioactive test charge source. Other thing is that they use, instead of using metal, they use glass. This is secret. And they've gotten so cool with it, or so precise with it, that they can not only do acoustics, but they can use a scintillating material and not only get the acoustics, but they can observe the light flash that's produced and use those to not only get calorimetry, but get triggering. So that's what you're seeing here. This is a DAC, the order of seconds. And this is the pressure. So this is the pressure drop you need to actually go sensitive. And then they look at the acoustic amplitude zoomed in, and these red spots are the light signals. So you can time both of these together, and the amplitude of the acoustic signal gives you the energy, and the amount of light deposited also gives you the energy. So you've now got competing measurements of energy, as well as the bubble that you photograph. So these are just things that I'm considering. I won't talk about them now. Well, I might talk about them if I come chat with you, but a lot of really cool ideas. So the idea is that, oh, what's up?
So how do you couple that with the cameras that photograph the event?
So you have to know when you're going to be sensitive. And that's difficult. It's difficult for a facet one. It's not difficult. It's, all right.
I think you can correlate that, but after after the fact, I guess you have two sets of data, right?
Yeah, and then you would have some DAC to correlate the time. But for the dark matter chamber, what you just need is exposure. You need quiet exposure. So the more time you can stay sensitive, then you're good. But for a fast cycling chamber, you actually probably need the time to beam. Right. Yeah. And then everything would be coordinated through your DAC, which I don't think anybody used. Like, it's wild to me that we did these experiments and we didn't have like programmable logic controllers or DACs, right? Or if we did have DACs, they were all like NIM logic DACs, which I don't know if you guys ever used NIM logic. Yeah, can you imagine doing an entire experiment with NIM logic? Right? But that's what they did. That's wild. And you're shaking your head like you've done it. You've done it.
Me?
No. So this is where we started when we were thinking about doing this LDRD. We started with the scintillating bubble chamber. And what this guy has, it has the glass that I told you about. That's what this is. It's an inner chamber with your actual target fluid as a working fluid, which is this chlorofluoro, or this fluorocarbon, excuse me. And then you have your pressure vessel, and you have your hydraulic actuator. And this is, again, a clean style inner jar. It's refrigerated, it's at a lower temperature, so at 130 K. Hydrogen operates around 20 K. And again, tubable lifetime is about an hour. So when we first started, we wanted to take this idea, clean out everything inside, polish it, put a hydrogen, and say, we're just going to cycle way quicker, so we don't have to worry about being as clean. And this was the vacuum jacket that we started with. This was like, I think I got this LDR in 2022. September is when I started. It's been like 15, 16 months. And this is the initial project scope. It was called the MMBC when we first started. Now, the idea was just to get everything, all the pieces together, because just ordering these things, like to get a 20 K or 20 Kelvin refrigerator, it's a pretty weird temperature that you need to be at, because nobody really uses hydrogen anymore. And the only other thing that's around there is maybe neon. I don't really hear people using neon for that much either. So you have things that can go much lower but deliver much less power, or things that can go much higher and deliver way more power. But 20 Kelvin is a pretty hard spot to get. And we were able to find one. There are a lot of other things we did as well. But this was the entire scope of the project when we first started. And this is where we were about 3 or 4 months ago. No? Yeah, about 3 or 4 months ago. And we're still here because we haven't finished, because we've done so many things. There are so many things that can be improved. So for example, the old bubble chambers used hydraulic actuators. We can use an electric one now. We didn't know we could do that. So we went and we ordered one off the shelf. And it took us like 2 months to figure out we could actually do that. We could actually like get the amount of force we needed to compress a liquid. That's a huge step up, because it's how many of you guys know car engines? You might know car engines. So the way your car engine works, you have a cam, and that cam makes your cylinders go up and down, but it's a fairly imprecise process. Imagine if your cams were digital, right? That means you can have basically any design you want, or any duty cycle you want on your bubble chamber. So if you want to cycle it quickly, you can do that. If you want to cycle it slowly, if you want to be really slow. So we're producing advances for the dark matter chambers again now, right? Turns out there's a company that they make windows that can survive underwater. So they can also make windows that can survive pressure vessels at 200 PSI, and they will guarantee it won't leak with hydrogen, right? Maybe they should have made was it the underwater horizon? Right, and I asked them about that, and they were like, well, if we had made it, it wouldn't have done that. And that's only 2 of the things that we figured out. I have an undergrad student who's like done all the machine learning for the image learning already. That time, so it's really cool. So the biggest question you have, or we have, is where we're going to put it, right? So this is the near detector hall. And as you can see, it's very well suited to the detectors that are already planned to be there. And that's also about 60 meters underground. And DOE does not want us to put hydrogen underground. They limit you to about 15 gallons. We're talking about 1/8 to 1/4 of a ton, right? So how are we going to get down there? I have some ideas. We could talk about it, not in the talk. But it did make me think about, well, what would happen if we couldn't put this in DUNE? And turns out there's more than one beam. There's LBNF, which has a particular structure, which is about the same rate as the old 15-foot bubble chambers. But then there's also the booster neutrino beam, which experiments like mini boon and micro boon and SBN are working on. And they have a different cycling frequency, which means if you want to be able to access all available beams, we need to be able to cycle quicker than the older experiments. And that electric actuator really helps with that. So what this has really turned into is an experiment called MAMBA. And MAMBA stands for the Modular Adaptive Modern Bubble Chamber Archetype. Because what we want to do is make a chamber. Sorry about that. What we want to do is make a chamber that not only can be essentially standardized, and you can make multiple of them and arrange them however you want, but we also want to be able to put whatever target we want in it as well. And we'll come back to why we want to put different targets in it. But if we do this standardized detector, we can essentially put a detector in all beam lines. Anyone that wants one, anyone that wants to build one, if we keep the price down, we should be able to do it. I think that's pretty cool. So what happens if we solve all this stuff? What happens if we do exactly what I say? Well, we get a new data set that will likely be the largest hydrogen and deuterium neutrino data set ever made. You can think of that as like the free nucleon data set, likely be the largest one that's ever produced. We resolve the tension and current experiments because we factorize underlying cross sections from the secondary nuclear effects. We also get rid of MEC. So we really are just resolving these three things. And then we can basically solve everything else once we get this. That means we are also able to properly constrain the largest neutrino data set ever made, which will be the one coming from DUNE, or probably the one coming from Hyper-K. We will be able to essentially take those cross sections and treat those nuclear effects in something like argon or in something like water. And then the critical thing is that we get deuterium measurements at all, which we also get minimum MEC and minimum FSI. So it really is a killer app for doing this sort of measurement. It really is a way to lead us in the, well, not lead us, but to really unlock the full potential of these new neutrino experiments coming out. So one of the things I really want to do is, again, put different targets into these detectors and put them in the same beam line, and you can start to do nuclear physics. So some of you who have done heavy ion work know what this is. Right? This is just looking at nuclear modifications. We can look at EMC effect, and this should be at the quark level. And it's literally just cross sections as a function of Bjork and X, as a function of your target. So Minerva tried to do this, but the smallest target they ever got was this CH. So it worked okay, but we could make it work better. Some of the other stuff we can do. So that measurement I showed you from Minerva with the TKI that was done, they actually use that measurement to do a proton radius measurement with neutrino. We can do that too. It would probably be way better. I don't know if it would ever approach the precision of the dedicated experiments. We could at least say something about it. And we could say something about it with hydrogen and deuterium, which Minerva cannot do right now. So the critical question is, I don't even know what sort of precision we can approach. I guess I'd have to actually do a study. But what precision could we approach? This is one of my favorite ones. This is one of the measurements that one of my mentors did. Her name is Geraldine Sam Zeller. So what she showed was that if you measure the Weinberg angle, which you get specific access to because you're looking only at the results of W and Z measurements, you get access to the W mass. I don't know if you guys saw this new measurement from CDF that came out that said that the W mass was 7 sigma, or at least their measured W mass was 7 sigma away from standard model. Turns out when you look at it from neutrinos, it's 3 sigma naively the other way. There's like a naive 10 sigma tension between neutrinos and collider. We could easily resolve this. We can do spin and polarization, this is just initial spin and polarization for diagnostics. If you care about measuring the output, if you do exclusive measurements, you can essentially break your cross section down into spin dependent portions and do diagnostic measurements again of your axial mass. And if your measurement is precise enough, This gives you another handle on making sure that you're actually doing your nuclear measurements correctly. Now, this is going to be controversial. What I've done is I put these two up because I want you to think about Q squared on the same axis. This is log Q squared, this is Q squared. This one comes out of this one. No, this one comes out of this one. This one comes out of this one, sorry. And this one comes out of this one too. Oh, they come from the same thing. Oh. But the idea is that you get a three-dimensional relationship between Q squared, neutrino energy, and Bjorken X. Essentially, you're trying to look at point scattering inside of the medium, cool. But what you also get are neutrino interactions that slide you into the non-perturbative region. And that's essentially why neutrino physics is so hard. The energy we've chosen is, I guess I would say it's in the practical non-perturbative region, which is why we have to do so much stuff to deal with it. So I think that LBNF DUNE is the experiment that can start to do these sorts of measurements. And one of the things we really want to put out of it, because we're looking at neutrinos, and again, neutrinos only use W and Z, we're getting precise understanding of PDFs of individual quark flavors. So these are the form factors. You take linear combinations of these form factors because these form factors are made up of individual PDFs from quarks. Linear combinations of these form factors should give you responses from individual quark PDFs. Which means if you want to pick out intrinsic strangeness with neutrinos, you can. It's really cool. And I think this is one of the ways that we can contribute to the heavy ion community, to the IC community. This is another spin and polarization thing. This is special to me because I did my thesis on TMDs, tried to measure Bohr molders on fixed target PP. One of the things you can pick out is this Bohr molders right here. This is essentially 8 terms that come from the Dirac projection of the quark. Is it the quark correlator? Do you remember? I think this is a quark correlator. But I believe it is this term right here. Essentially what you're looking at is the coupling of spin and orbit between quarks and nuclei. So I think in neutrinos, I think the only one we'd be able to pick out is probably the unpolarized. But if we were able to get, if we were ever able to get a polarized neutrino detector or a polarized neutrino target, which is something we could start thinking about once we build the initial bubble chamber, I think we'd actually be able to access some of these guys with neutrinos. Now, of course, we need tons of statistics, but it'd be cool. And I think we might be able to try to start thinking about the first TMD measurement with neutrinos, which I don't think I'd ever said. Or I don't think anyone would ever really say. And one of the reasons I really care about these TMDs is because this gives you a map to the generalized part-time distribution function. So we really do have a path. I think it needs to be better developed, but I think we really do have a path where neutrinos can fundamentally contribute to this full understanding of the proton or neutron. And the critical question is, do we have the statistics? Because I believe the actual physics is there. So this is where I'd eventually like to take this, and this is what I mean by background Fermilab and doing nuclear physics. I think if we take enough data, some enterprising grad student or postdoc is going to really try to sit down and figure this out. So in summary, I think our current cross-section sample underlying the event generators is too small. We need to find a way to increase it. Our next generation of experiments will have strategies for dealing with our uncertainties and cross-sections. But I think the best way to do this is to just build a bubble chamber and put it in a place where we can get tons of events. And if we do that, we get tons of benefits from it, including, I think, complementarity to the EIC. So that's the talk. What questions do you have?
It's about what neutron backgrounds in this kind of bubble chamber are they like a significant issue or
Neutron backgrounds. So I think neutron background, I don't know if we're going to be sensitive enough to really have to deal with background neutrons as a real thing. I think the major issue we're going to have is actually finding the neutrons that are coming from the signal events that we want to measure, right? Because they're probably not going to show up in the bubble chamber. That's one of the things I want to try to address with the test chamber. So MAMBA, essentially when we finish it, is going to become, the small version is going to become a test chamber. The thing I'm going to think about laser holography for one of the other ideas I've had is actually to try like a lithium-based scintillator that we could try to do neutron tagging, right? And that would be like scintillating. We would use essentially the dark matter scintillating idea to like do this neutron tagging, which gives us so much flexibility. I think it'd be cool.
Yeah.
So I don't know if neutron backgrounds is really a problem in the field, but the neutrons in general are an issue.
Mhm. Yeah, I'd be curious to see eventually you can put this thing in the beam line. You have to worry about like correlated, neutrons from up beam interaction here.
Mhm.
But I guess I don't know about bubble chambers to know if that would be an issue or not.
Yeah.
So yeah, great talk. So I understand you don't want hydrogen mixed in with the other targets, but you already have an argon detector there. Is anyone talking about putting hydrogen in that, taking it out and doing a differential measurement of the
So
gathering of the
you
hydrogen?
want to put hydrogen in the TPC?
Yeah, the reason is like the dark matter, like LZ has this hydrox thing where they're gonna put hydrogen and xenon because they want a light target. Seems very similar here.
But the critical question is how much hydrogen are they putting in?
A lot, like percent level by mass or something.
You're right.
It's not 100%, but it's uses the existing detector.
So the reason they're putting in percent level is because above 4% you get flammability,
Okay, yeah.
right?
There's also a solubility. I don't know what it is.
Yeah.
Yeah, I think they try to put as much as it's soluble.
Yep, that too. But the critical thing though is I don't know if I would put hydrogen in a TPC. And I have heard people say that they've done it. That is not a risk I would take. Because as soon as I've seen TPC spark. When they spark, there's a lot of electricity. If you spark with a leak with hydrogen, I don't know if I would do that.
That's it.
Yeah. Any other questions?
I have a question. I mean, we have to stop recording for this or something, but you said that you can't put the hydrogen above a certain size underground. Seems like that's a critical thing. And you mentioned that you had a solution for that.
Yeah.
Can we talk about that?
Yeah, and we don't have to stop recording. I just don't want to put it on slides.
Okay.
This is gonna sound really funny, but right now in NOvA, we have an access tunnel that is just a open 30-meter tunnel that goes from the surface to the actual detector or to the level of the detector. So what if we just dug a giant hole and we're gonna close it? You could technically say to DOE it's not underground. But the critical thing is that if something does explode, I was joking, if something does go up, there's enough circulating air, there's enough place to dissipate the energy that it'll just go up the shaft. And if you think about it correctly, that's an easy way to dissipate all the energy without being super dangerous. Now, of course, you don't want it to do that, but let's say, God forbid, something happens, the perfect confluence of events happens where it does happen. You need to make sure that nobody gets hurt if that does happen. And that's always been one of the primary things we've been thinking about as we've been building this thing. So the current winning idea is even if DOE would allow me to put something in the near detector hole, I wouldn't do it. Because if anything goes wrong, the entire DUNE near detector is dead, right? So, I'm not going to be that person.
That's one more silly question. Did they ever blow up any of the old bubble detector chambers or some of them? Yeah. Okay.
Yeah. And one or two of them killed people.
Oh,
Yeah. Like it can get like,
yeah.
here's something I noticed as I look back at old papers. Physicists were cowboys back then. They did wild stuff, man. I mean, like one of the original neutrino detectors was like Project Poltergeist, and they put like an emulsion detector like underground next to a nuclear bomb. And they were like, let's just do that. That's a great idea. So yeah.
Yeah, your EIC ideas are interesting, and they, from part 1, 2, and 3, they get progressively hungrier for statistics.
Yeah, that's true.
So for part 1, have you tried to estimate statistics that you would need, whether it's even possible with neutrinos?
I have not. I haven't gotten that far yet, but that is something that I'm thinking about. And one of the easiest ways to do it is just to look at what sort of resolutions I would need for the unpolarized. I mean, that's where I would start, right? And then see how much I would need.
I mean, theoretically, I think you're right. I think experimentally is the big question.
Yeah.
If there are no more questions, thank Brian again.